Alright, we've talked about collisions between objects before in terms of momentum. I'd like to now talk a little bit about collisions and energy. If you're going to figure out the motion of objects in a collision, you actually need to use both of them, but the energy comes in different ways than the momentum does. So suppose I have two objects, mass 1 and mass 2, and they collide. If we look at these as a system, that's a system in which there are no external forces on it. We know that the change in the momentum of the system over the change in time is equal to the sum of the external forces. And if this term goes to 0, then that means that the change in momentum of the system is equal to 0, and the momentum is a constant. So this is the conservation of momentum of the system. And the momentum of the system is just the sum of the momenta of the objects. So P system, that's a vector, sorry about that. The momentum of the system is equal to the sum of the momenta of the objects. So this is, if I know the momentum of the system before, sometimes I can calculate the momentum of the, I can use that to calculate the momenta of the individual objects afterwards. You may also remember that at one point we said that another way of saying this is that the velocity of the center of mass is constant throughout the entire collision. So let me illustrate how energy comes into play. We're going to take two very simple collisions. First one is billiard balls. Two objects that have equal masses. And so here's the mass 1, mass 2. Mass 1 is equal to mass 2. And let's start off with, this has a velocity v initial, and this velocity is 0. So this is what happens on a billiard table. You have a cue ball, it hits another billiard ball, and if you hit the, if we just look at it in one dimension, what's going to happen after the collision is that M1, the cue ball is going to be sitting there, and the other ball goes off with the same velocity that the first ball had. If you don't believe me, go find a pool table and try it out. Is momentum conserved in this? Well, if we assume that we're not having any interactions from the forces that are holding these masses up, we can write down that the initial momentum for the system is just equal mass m1 times its velocity v sub I plus mass 2 times its velocity, which was 0, and by conservation of momentum that must be equal to the final momentum of the system, which is going to be equal to m1 times its final velocity plus m2 going off at a velocity equal to the initial velocity of the cue ball. Right, and we can see that if the masses are equal, then the initial momentum is indeed equal to the final momentum. Okay. The other question we can ask is, what happens to the kinetic energy of the system? Well, the initial kinetic energy is just equal to 1/2 m1 times its initial velocity squared. There's no kinetic energy involved with this mass. And the final kinetic energy just happens to be the same thing. The final kinetic energy is equal to 1/2 m2 v initial squared, and if m2 is equal to m1, then the final kinetic energy of the system is equal to the initial kinetic energy of the system. And let me underline that these are the kinetic energies of the system as a whole. Okay? So this is what we call an elastic collision. In fact, a completely elastic collision, the energy of the system is equal to a constant. And in fact, I should write this more particularly. I should say that the kinetic energy of the system is equal to a constant. All right, so that's a very simple collision. Everybody's seen that. We conserve momentum, and after we conserve momentum, we can note that in this case, the kinetic energy is the same before and afterwards. The other extreme would be if we had a collision between two equal masses, but they're not billiard balls, but say chewing gum balls. And so we'd start off with one wad of chewing gum over here, hits another wad of chewing gum, no, never mind how we got this situation. And when they collide, they stick together. And so we end up with these two masses stuck together, going off at some velocity v final. Okay. We can find out what the final velocity is by using the conservation of momentum. So the initial momentum of the system is just equal to m1 times v initial, okay? And the final momentum of the system is just going to be these two particles together. So we've got m1 plus m2 going off at a velocity v final. And if the masses are equal to each other, we would get that v final is equal to v initial over m1 plus m2. So that's equal to v initial over 2. So that would be the final velocity of the two chewing gum balls going off together. What happens to the kinetic energy in the system? Well, the initial kinetic energy of the system is just equal to 1/2 m1 times v initial squared. And the final energy for the system is equal to 1/2 times m1 plus m2 times v initial over 2 squared. That's the final velocity of those two together. All right, and let's see, so we've got, this is equal to 2 times m1, and so this is equal to 1/2 times 2 times m1 times vi squared divided by 4, and we end up with the final energy is 1/4 m1 vi squared. So in this system, we end up with less kinetic energy than we had when we started off. Okay, this is an inelastic collision. That means that the kinetic energy is not a constant. Okay. I should underline that. Okay. We've still got kinetic energy left after the collision, but we've lost half of it. Where did it go? Well, it went into the deformation of these chewing gum balls. When they hit each other, they stick to each other. There's energy of adhesion. They heat up. There's all sorts of ways that this system could absorb energy. So the rule is that in a collision, you can almost always, 99.9% of the time, conserve momentum, but you need to be very careful about conserving energy. Sometimes you can conserve energy, but most of the time you cannot completely. In the real world, you never completely conserve energy. Energy is conserved when you have collisions between objects that are very rigid, for instance, billiard balls, ball bearings, very elastic objects, and things that deform a lot always lose energy in the collision. Okay? All right.